So when we talk about a graphical method of graduation, we are primarily looking at plotting. We are looking at plotting the crude rate estimates directly. No formula, no standard table. So for different age groups, here I am taking the age here and the crude rates here. Crude rates which came through our estimation mechanisms by observing the experiences or the data. So I could plot even a discrete mortality rate QX or a force of mortality, instantaneous force of mortality mu x, whatever it is. At different ages, I am trying to plot the crude rates first. I am trying to plot the crude rates and probably try drawing a kind of a smooth curve across the edges, a quick curve across the edges. But of course, this looks easier to talk about. But when points are completely ad hoc, drawing a smoother curve is always a difficulty. Drawing a quick freehand kind of a curve is always a difficulty. But even from a lookout perspective, if I am looking out for quick and dirty result, a quick and a dirty result which has nothing to go with a formula, which has nothing to go with reference to any table, only our crude experiences, but at the same time quickly making a line, quickly drawing a line or a curve across all the plotted points. So more, this is purely more and more from a visual impression kind of a perspective. We are trying to bring this up, and of course this will have so many drawbacks. May not may testing for actualities, testing with respect to any parametric formulas. There's no base to it. It's just an observation and a smooth line drawing the observation. So this is more and more based on the experts curve drawing skills, right? And it is more and more subjective also, right? An expert across the same point could draw a smooth curve like this, or someone else could go more like this. So the values are more and more subjective, fair enough. But when we are looking at quick and easy to understand kind of smoothening of the crude rates, even this is one of the processes that is typically followed. So in this, what is that we are going to do? We are looking first. We are plotting all the crudes, right? We are plotting all the crude estimates, QX or MUX, whatever it is. And when we are trying to plot the crude here, probably we talk about two major mechanisms. One being the plotting is on a linear scale itself, whereas the other one is trying to plot the same on a log linear kind of a scale. The reason being, in case of human mortality, we see that the mortality rates are very low. In case of the mortality rates are very low in case of very smaller ages, whereas they are very high in case of higher ages. Now, if all these rates have to be plotted on one single graph, probably because of the range that they are operating in, the scales required are much higher, and because of which I require a very huge graph paper if I have to accommodate all of them on the single graph itself. Whereas when I take the logarithm of their values, instead of taking the values as such, if I take the logarithm of those values, sometimes it may come out that the logarithm's range for the same comes down into a very narrow range. And because of that, plotting on a single graph paper becomes more and more easier. So if at all I have to, I'm coming across a scenario where I need to develop this graduation right from a very early age, let's say 20 years up to a very high age, let's say up to 80 years. Rather than relying more on a linear kind of a model, I prefer relying more on a log linear kind of a model. But otherwise, if I am looking at between, let's say, 30 years to 40 years, developing a kind of a graduation mechanism, even a linear model is quite adequate and sufficient in that particular process. So wherever my intention is to do the graduation over limited age ranges, I can still prefer the linear scale. Otherwise, it's always better to go with the log linear kind of a scale. And in some cases, when I'm trying to plot the same for a few ages, probably very high kind of ages or probably very low kind of ages, the mortality numbers are probably the overall data itself which we are observing could be very scarce, right? Probably at let's say 85, 86, 87, the data of the population which we are observing itself is very scarce. If that is the case, we talk about do not plot for each and every age separately, do a plotting for a group of ages. And the way you would like to group, though there is no hard and fast rule that you have to group in this particular manner itself, make the grouping in such a way that across the group the rates are going more and more smoothly, and if possible try to go with evenly spaced group. And when we are doing a plotting for that group, probably if we are saying for every 5 years I am creating an age group, right? So probably 20 to 24 is one age group, 25 to 29 is one age group, 80 to 84 is one age group. So when we are trying to do a plotting, probably you try to plot the mortality experience, one either against the mean value of that age group, so in this case probably 22, or you could take a weighted mean where the weightage can very well be computed based on their exposure to risk. So if many observations are there at 20, then lesser at 21 and so on, lesser at 24, then the weightages could very well be taken based on those to identify the number associated number that is corresponding to the plot for the crude rate. But what is generally suggested is go with an evenly spaced kind of a data, and make sure that in each of the groups the number of deaths in each of the groups is at least reasonable, not just one death or half a death in each of the group. Try to make it that the number of groups, number of deaths in each of the groups is reasonable. Probably 5 is what we generally look at it as a reasonable number of deaths in each of the groups. Otherwise you may have to again further get into the regrouping kind of a process. And for each of the groups, first of all, because the graph requires age or age group on the x-axis and the crude rates on the y-axis, the age could be a weighted average or a simple average of the ages, and against them the plot of that particular group's crude rate is taken, and a smooth line is drawn, freehand drawing is drawn, which could identify that these are the smoothened or graduated rates based on the crude rate. But slightly more than that, apart from the points that we have identified, we will also talk about a 95% interval across these points. How do I identify the 95% interval? Identify a 95% interval across these groups. How do I identify this 95% interval? Probably I can take the standard error around it. Whatever is the crude rate I am getting, I could talk about it as plus or minus square root of dx by ex. So this is the expected exposure to risk for that particular age group, and these are the number of observed deaths. So using this kind of a mechanism, or probably when I am using mu x, I could look at it as mu x plus or minus 2 square root dx by central exposed to risk. Any one of these mechanisms I could very well use to typically come out with a 95% interval. So corresponding to each of the ages along with the point, I am also identifying a 95% kind of an interval. A point, a 95% interval. Let's say this is how I'm getting my point. Now what we are saying is, now a graph that I'm trying to draw, a smooth line that smooth curve that I'm trying to draw, it should pass through the 95% interval of majority of the observations, though it may not be mandatory that the curve that has to pass through all the 95% intervals. But if we are talking of a 95% interval, probably it's like 1 in 20. 95 meant the remaining 5%, which is like 1 out of every 20 points may not come on this curve, but definitely 19 of these ranges, if my 20 age groups are present on this, at least 19 of them should cover this particular curve. The curve should pass through at least 19 of these confidence intervals. Even if one of them is not passed through, that's not a big problem. And that is where we talk about, okay, I could have drawn a graph like this. So all kinds of smooth curves can very well come out, and that is where the decision of the expert also comes into picture. Now once I am making a graph, try to draw it as smoothly as possible, because we are more interested in smoothening out across the various age groups. So this is where the art comes into picture, right? So the more the experience that is getting built up, the more effective the rates are going to be created, the more effective graphs can be drawn based on the final understanding of how in reality the rates at different age groups are going to perform. So the more and more the experience comes up, the more and more the practice comes up, a better graphs can be generated in this process. But try to draw as smooth of a graph as possible. And based on that, okay, now that the graph is in place, okay, I'll look at 22 years, 23 years, what are the rates? Okay, this is for 22, this is for 23, this is for 27. So I am getting the values corresponding to each of the integer ages, probably rounded to 2 decimals or 3 decimals kind of a stuff. I am able to get the rates from the curve. I am trying to generate a table of rates for each of the age groups. And once I have the rates, then probably those are my graduated rates generated from the crude rates using the graphical method. And of course, just like the way we have tested the graduated rates with the actuals using the statistical methods, goodness of fit mechanisms can very well be employed. The chi-square test, the science test, grouping of science tests, we can very well test out all those kind of mechanisms to see the adequacy of or goodness of fitment of this particular model. And obviously, if the data is very small, probably statistical tests may not be a good process here. Rather than that, a simple visual inspection itself could be more and more appropriate in terms of understanding the fitness as well as the smoothing. And what you can do is to test out the other alternatives as a part of any testing processes, any testing strategy. If I am looking out for different kinds of alternatives, probably I can keep redrawing the graph. Probably this is one graph, this is the other graph, or I could say why not this. It is passing through all of them, but this is the graph. But so like this you keep generating different kinds of graphs to see which one is more and more adherence to that data, and based on that whatever the graduated rates are coming out, do a hand polishing of those graduated rates by making some minor modifications and adjustments to the same, so that both smoothness as well as the adherence to the data is coming out more and more effectively. So that is how we try to look at doing the performing the graduation using a graphical method. Now that we know all these three methods, the graphical, the standard table, as well as a parametric formula kind of an approach, I would like to see a comparative assessment across these three different kinds of methods for performing the graduation. All right. So on a comparative note for the three different methods, one statement that I can make at the offset itself is for all kinds of data, for all kinds of data, there is no one single method which is the best fitment kind of stuff. For some of them, probably the parametric formula approach is much better. In some cases, I see a standard table reference is much better, whereas in some of the other experience model building cases, the graphical method is also more appropriate, right? So typically, if I have to start off, if I am having large data set, if my data is very large, probably I can quickly look at building up my own parametric formula with a detailed number of parameters to bring in more and more smoothness as well as accuracy into the graduated rate. But if I am working with very scanty or scarce kind of a data, then probably I see either referencing to a standard table kind of an approach or using the graphical graduation kind of an approach are more appropriate compared to a parametric formula kind of an approach. So that's the reason we need to understand the comparative advantages and disadvantages that are associated with each of these methods of graduation. And from that dimension, if I am looking at the benefits as well as the limitations that are associated with the usage of the parametric formula kind of a method. Probably if we try to understand this parametric formula kind of a method, it more looks like the probability models, the probability distributions which we look at different ages. Probably it looks like a natural extension to the probability of death that we are trying to compute based on the hazard rate, the probability models for different ages across different points in time. So that is what is coming out through this parametric formula kind of an approach. So I can use that kind of formula to extend across any kind of ages. I can test them through good statistical estimation kind of models, right? Formula wise, one single formula more like a distribution, and the testing becomes more and more appropriate, and probably even it could be automated quite comfortably using a software program kind of a scenario also. And in case the parameters are not too high, parameters are reasonable in number, not too high or not too low, probably a good model can be constructed which can adhere to the data quite effectively, as well as a proper level of smoothness is also generated. So we can work out on the various possible models using various parameters, and probably one of them could be a very decent fit to our data, both in terms of adherence as well as being smoothened out in the process, right? And probably what we are also looking at is whatever the computer program can generate, we can even think of assigning the weights in terms of arriving at these parameters, so that they reflect more and more closer to the reality, not just a smoothening, but even a reality wise they come more and more better to work out with. And they are much better in terms of comparisons, because I am using similar kind of a distribution, right? So I am using more or less, if at all I want to look at the experience comparison of 2014 versus 2018, I can use the same formula for the data of 2014 and same for 2018, and from them I can look at the differences or the errors that are coming out with respect to my formula, and see whether the experiences are improving or deteriorating. So when one formula is there in place, the comparison of the experiences, probably male versus the female, comparison of the experiences become more appropriate, as I am trying to fit the same formula for different kinds of data across different periods of time. So highlight understanding how the experiences have changed, improved or worsened, or those kind of stuff become more and more easier when I am working with parametric form of formulas approach. And at the same time, the major reason why I look at the parametric formulas is probably a standard table can be prepared, because when we talked about the standard tables earlier, we said that they are really more authentic kind of tables. They are prepared based on significantly sufficient or significantly large volume of data, well well defined kind of a data. So they are really an important factor in terms of preparing standard tables also. So from all these dimensions, we can easily see the positives from a parametric formula perspective. But on the flop side, what we could very well see is this parametric formula approach works well only if my data is large. In case of scanty data, in case of few of them, probably deriving the parameters itself will become a massive exercise. So it may not be a good fit in terms of either error minimization model or likelihood maximization model for the identification of the parameters may not be a good thing if I am going with a very limited data set. And more than that, the problem which people see with the parametric approach is there may not be one single formula. See, parametric approach is more to go with a formula, right? So there may not be one single formula which can fit the experience of all ages. Because as we are saying that this mechanism is good if the data is very large. In real world, what we observe is the experiences are very large in the Middle Ages. But as we go more towards the extremes on the either side, the data becomes very scanty, and even the mortality curve probably are towards the much lesser ages or much extreme ages, the behaviors are completely different. Either we can talk of infant mortality here, or we talk about towards the end the mortality rates at very high ages, the mortality rates are drastically higher, or probably within the various groups itself there could be a lot of heterogeneity that is present in the data. And because of all these reasons, whatever is the group that I have taken, whatever the age group I have taken for the fitting of the formula may not be easily extendable because of all these kinds of changes in the mortality rates or heterogeneities that are occurring across the different age groups. And even the behavior of the data, the behavior of the different age groups is completely different. So one single formula may not be anywhere closer to good fit, especially if I have to do some kind of simple extrapolation kind of mechanism. First, I do the predictions for middle ages. I create a model for based on the data used for middle ages and try to extrapolate for both the sides. That may not be an appropriate or a best fitting kind of a mechanism that we are trying to do. So that's where, if at all, I'm trying to extrapolate beyond the ages where the data is more and more scanty, I have to really take enough care to work out when I'm going ahead with the parametric formula kind of a mechanism. Correct? So from that dimension, what we typically see is there are some kind of an advantages associated with the parametric formula approach, and equally there are some kind of disadvantages associated with the same. But on the other side, now when I start looking at the reference to a standard table kind of an approach, as we have initially discussed, the standard table as well as a graphical mechanism are more and more appropriate even when the data sets are very small, because we are already referencing to an existing table. We are trying to do the fitment of the observed rate with respect to an existing standard published table. So we will not deviate very drastically from the experiences that are there in that published table. So as long as a comfortable model has been fitted between the existing model based rate, existing standard table based rates and our observed rate, the graduation becomes more and more easier of a process. So as long as I am able to choose a simple formula, could be as a linear regression kind of a formula or a basic exponential kind of a formula where the degree is very much on the lower side, 1 2 kind of degrees, linear, quadratic, nothing more than that. As long as I am able to find a linking function between the actual observed rates and the table based rates, as long as I am able to find a simple linking, smoothing is quite comfortable. Only when I am not able to find a better simple formula, that is where I would be worrying about the smoothness from the standard table model. But of course, as we are working with very limited sets of data, this kind of a model cannot be used to produce another standard table, because the standard table production can depend majorly on the observations of the large volumes of data. But here, when I'm using one standard table, I can generate a mortality experience for my observed product line. But generating another standard table experiences through this mechanism is nowhere closer to reality. And more easier and more flexible because of both the simplicity in terms of formula as well as in terms of the data set that are available. And just by looking at the standard table that I am using, I can get a quick look at the overall shape of the experience, because anyhow I am seeing that a quick look at overall shape of the experience, because anyhow I'm quickly looking, I'm seeing that this particular standard table is more appropriate to my particular experience fitting. So the moment I see the shape of that particular standard table, I can very well visualize more or less on a similar grounds will be something that is associated with my particular model fitting process. But as I said, it's see there could be so many standard tables that are published, right? The tables that are there, there could be a lot of national tables which are published, or there could be some tables, some standard tables that are published based on the experience of the insurance companies. So there are so many such kind of tables that are available. Unless I am very clear on what is the correct table that will be appropriate to this particular experience, unless I am able to identify it, the benefit of using that table for a graduation process is not getting met, because the more and more wrong tables or inappropriate tables that are being chosen, the overall graduation experience itself will lead into complete complexities, are probably either resulting in very heavy overgraduations or very heavy undergraduation, and thus not meeting the purpose of the graduation from our dimension. So that is where one more dimension I would like to look at from the graphical methods perspective. What are the benefits and the disadvantages associated with each of them? So looking at the graphical method, as I discussed earlier also, both the graphical as well as the standard table approach, they are more available, more appropriate when the data is very scarce. And the more beneficial stuff here is the flexibility as well as the experience of the analyst experience. So the physical experience of the analyst is something that is taken into consideration. It's more and more subjective. The analyst can understand the specific mortality behavior at one or two ages, and based on that, he or she could either increase the slope of the curve or decrease the slope of the curve. But whereas on the other side, when I am going with a parameter based or reference to a standard table base, there is a lot of mechanization in the process, where the flexibility does not come to the analyst. So that is one of the greatest advantages, right? So the more and more experience the person is able to build in terms of understanding the various features associated with the experience, various features associated, probably the accidental deaths or something, some specific disease related health problems. All these things, the more and more analysts can evaluate at a particular one or two age point, accordingly the shape of the curve can be taken into consideration. But when I am using more and more technically, mathematically sophisticated kind of an approach, then all these things cannot be implemented. That's one prime way I could see the positivity in a graphical kind of a method. But what is happening is, because of that hand drawn kind of curve, either I may see that the curves which are being drawn either will be more and more smoother but not adhering to the data, or the vice versa can happen. They can be more and more adhering to the data, but they may not be more smooth. Because of that, multiple attempts, multiple iterations in terms of the drawing of the curve or making physical adjustments to the data, physical adjustment, that is what we call as the hand polishing. These kind of things may have to be done to try to bring in more and more smoothening as well as the adherence to the data, which means finally it's the experience, it's the art, it's the skill, and along with that more and more of patience. I cannot run them through a computer. A program cannot be written to execute the same. All these things will act on the flop side for this graphical method. So more, and because of the more and more subjectivity that is being brought into this graphical method, though there is an advantage on one side, we see that any kind of wrong assumption that is taken up by the analyst or that is taken up by the modeler could result in graduations badly affected from the actual experiences. So resulting in a very much over graduations or under graduations. Though we say that the data if the data is scarce, I am able to use a graphical model, but too much lower, I don't know what shape I have to draw. Probably if you see here, if I just have only 2 or 3 points, probably I may draw this shape or I may draw this shape. So because at the end it may pass through 2 points, may not pass through 1 point if there are only 3 points. So very scanty kind of a data. What kind of shape we have to bring into that curve becomes more and more a complicated kind of thing. So that is one more area that needs to be looked at. And when the moment I am taking the opinion of different graduators, different modelers, they give me different shapes. So overall, arriving at one unique kind of a solution may be a very difficult thing in this particular process. And of course, just like a standard table approach, it is not suitable to typically prepare any other standard table, because as we know that to prepare a standard table, I need to work with large volumes of data. And when we are trying to find out for each integer ages the actual experience, or for each integer ages we are trying to look at the graduated rate based on the scale that we are using, how many significant digits after the decimal point, what is the minutest scale that we are using, we can work out only to that layer. Probably if I want 4 or 5 digits after the decimal point, it may be very difficult to achieve through the graphical method, whereas the same can be very comfortably achieved using either the parametric formula approach or the standard table approach. So, just in a quick nutshell, it is very clearly understood that no one single model can be one single approach of graduation will be a best fit for all the data scenarios. As we have seen, in some cases the graphical method is more appropriate. In other cases, the standard table approach looks more reasonable, and wherever I have large data sets, or if my intention is more of a generation of a standardized table, then probably I can very well look at reference or creating a parametric formula for the graduation purpose, right? So the understanding of all these advantages and disadvantages, the limitations of each of the methods is very much required in case I have to end up with coming out with the best fitting mechanism which can provide both, which can balance very comfortably between the smoothing as well as the adherence to the data, right? Now that I have completed, let's say, the comparisons, and I have chosen one particular method out of those three for performing. I have chosen one particular method out of the three for performing the graduation. Then we are looking more and more in terms of, once we have arrived at the graduated rates, what are the various statistical methods that are available or statistical tests that I can do with respect to the graduated mechanism that I am using, so that the adherence to the data can very well be tested. We have looked at the chi-square test or science test or grouping of science tests earlier, which are some of the mechanisms that can very readily be used to check out whatever the graduation, whatever is the mechanism that we have used for the graduation, whether the graduated rates are more or less in sync with respect to the actual experiences that have come out. But apart from that, we would also like to see what other statistical tests play a key role here. We'll just take up those activities to try to understand the appropriate statistical tests for graduation. All right. So when I have to use this chi-squared kind of a statistic here, I am primarily looking at what are the actual number of deaths for each age, and what are the expected number of deaths coming through your graduation process. Right, I am trying to find out the actual number of deaths and expected number of deaths, and at the same time trying to compute the chi-square statistic. The chi-square statistic directly comes out as the actual minus the expected whole squared by expected. That is what typically comes out in case of the chi-square statistic. So we are trying to compute the same. The actual directly comes based on the experience or based on the observations. Whereas when I am talking of the expected, depending on the method that I am using, in case I am going with QX, I get the expected value. I get the expected as the whatever the initial exposed to risk. I multiply it with QX, and so that is what is coming out as the expected value. And in case of finally when I am dividing it by the variance or the standard when I am dividing it by the variance, see when we are talking about a Z statistic, we talk about the actual value minus the mean by the standard deviation or the square root of variance. So in this case, the variance is coming out. If I am going with this mechanism, the variance is nothing but NP. If I am saying this is NP going with the binomial model, the NPQ, which is the variance, is going as EXQX 1 minus QX for the graduated rates. So what I can do is I can compute the Z values for each one of them. I can do a Z square for each one of them, and probably I can add up all the Z squares at all ages and say that is equal to my chi-square. Or similarly, I can if I am using mu instead of q, then we are looking at the actual number of deaths. Then it is going with respect to the Poisson distribution. So the expected value with respect to the Poisson distribution is central exposed to risk multiplied by mu x plus half. So actual minus the expected whole squared, and that is what I am dividing by the variance, which is again the same in case of Poisson, central exposed to risk multiplied by mu x plus half. So using these mechanisms, I'm trying to add up all the values across all the ages to finally arrive at the chi-square value in this case. Right? So any graduation, if I have to test, I am looking at the actual number of deaths at different ages at each age group or age, and then I am comparing them with the expected number of deaths. So that is what is the chi-square comparison that we are doing. And one more thing is, now if I have to make a conclusion regarding the chi-square, what are the degrees of freedom that I need to use to make decision. What is the degrees of freedom that I typically need to get it? So for that, there are a few mechanisms to talk of. In case I am going with the parametric formula kind of a mechanism, what we are saying is start with the number of age groups that you have. Number of age groups or ages that we have considered. So let that be the degrees of freedom. But depending on number of parameters that you have estimated, let's say if I am calling it as k, then what we are saying is the degrees of freedom which you use for the chi-square test is n minus k degrees of freedom to really say whether the graduated rates are more or less a reflection of the observed rates or not. So that is what we do in case of a parametric formula kind of an approach. But if I am referencing to a standard table instead of a parametric formula, if I am referencing to a standard table, again I'll start with number of ages or number of age groups that are being considered, that are being evaluated. Let's say I'm going with the n. Again, the number of parameters that we are estimating, because there also we use a simple formula relation to estimate the parameters. If you remember, the way we have gone for is, let's say I'm talking about the graduated rates qx. We said let them be something like a plus b qx with respect to a standard table. Means here I have two parameters to be estimated. That is what I am calling as k. But apart from these two things, the choice of the table, which standard table needs to be used. For this choice of table and the constraints that are associated with respect to this particular choice of the table, we are losing some more p degrees of freedom. So overall, when I am going with a standard table approach, I would stick to n minus k minus p degrees of freedom for making decisions with respect to whether the graduated rates are more or less approximating are a good fit to the actuals or not, right? And when I'm using the graphical method here, that's even more challenging. How many degrees of freedom I have to use, because the calculations more or less the same. The actual deaths minus expected divided by that variance. Actual minus expected whole square divided by the variance, which I can very comfortably take. In case of a graphical graduation mechanism, I'm talking of it's more of approximative kind of a mechanism, wherein it says that for every 10, somewhere around 10 ages that are fitted, reduce 2 to 3 degrees of freedom. So probably one associated with height, one associated with slope. So reduce a couple of degrees of freedom, or probably one associated with curvature. So just to address all these elements, typically reduce 2 to 3 degrees of freedom for every 10 ages. So probably if I am trying to fit around 20 ages, around 4 to 6 degrees of freedom can be reduced, and I can say that around 14 to 16 degrees of freedom is what I will take for making my decision. So these are this is an important attempt in terms of using the chi-square test for doing the for testing out the graduation, whether the graduated rates are more and more appropriate or fit to the actual observed kind of rates or not. You, depending on the mechanism that we have used, either the parametric formula kind of an approach or a standardized table kind of approach or graphical method, based on that we will be trying to removing the degrees of freedom, starting with a base which is the total number of ages that we have considered. And so the other kind of mechanisms, as we have seen earlier, also I could go with the cumulative deviations kind of tests, or I could look at the science tests. All these tests can very well be looked at. All these tests can quite comfortably be looked at. And the other important point that comes into picture as a part of this session for me is, what if there are duplicate policies, the same person taking multiple policies? So if that person had died, probably it is looking as if my actual number of deaths will show a higher number, because it's the same person who is having, if I'm looking at it from a policy standpoint, because he is having 5 policies, it looks as if there are 5 deaths that have occurred. So that is where for modeling the experience correctly, for doing a graduation of the rates in a more appropriate manner, the duplicate values need to be addressed quite comfortably. And that is where probably I may not, it may not impact the expected number of deaths. Expected number of deaths may not be impacted very heavily because of the duplicate claims, but the variance in the number of deaths is certainly going to increase drastically. So this is where any statistical test that comes up, probably where we are talking of actual minus observed whole squared by divided by the variance. If the variance is going more and more higher, the null hypothesis which need to be rejected may get ended up into fail to reject kind of a category. So that's where the decision making criteria can get very badly affected, right? Because one way we are looking at it is, instead of talking of number of person years observed, when I'm talking of the exposed to risk, I can look at it like number of person years observed and the number of deaths. Or the other way I could look at is number of policy years observed and number of claims, number of policies becoming claims, becoming death claim. This is a much more appropriate thing, and it can handle the duplicate policies quite effectively. So rather than looking at the measurement of the mortality experience in terms of persons and the number of deaths, we could very comfortably handle number of policy years and number of policies turning into deaths. So that is a much more appropriate thing, because one person having multiple policies can quite comfortably be addressed through this mechanism, right? Because from a life insurance company's standpoint, the settlement of the claims or the claim experience is based on the number of policies rather than the number of persons. So that is where the intention comes out. As we know that whatever the claims we are collecting, they are not independent claims, because the same person may be the insured in both the claims. So we are not dealing with independent claims, and the two distinct claims that have come probably could refer to the same underlying death of the person. So that is where we are bringing in the scenario of duplicate policies. And when we are looking at the duplicate policies per se, as we said, the expected number of death claims may not be very heavily impacted, but the variance will come out quite drastic. And that is where we talk about whatever the variance we are computing, right? Variance in the number of deaths. It is suggested that you bring in a multiplication factor, I square times pi I divided by I times pi I, wherein we are talking of the proportion of policyholders. When I am talking of I am more talking about the proportion of policyholders with I policies. So when I are talking of when a person is having two policies, so and that proportion is, let's say, 5% of the policyholders have two policies, then probably all we are saying is sigma the contribution by the ith two policyholders group is 2 squared times 0.05 divided by 2 times 0.05. And similarly, I will do it for three policy holders, four policies holder, five policies holder. This will adjust the variance of the number of deaths. So this particular pi I, where I am taking the proportion of the policy holders and I is the total number of policies by each of the policy holder, this adjusted variance whatever we are using, that I will take into the consideration for the computation of, or for the determination of the chi-square value and then making the appropriate testing process, right? So that is what typically is the gist of this particular session, wherein we started off with trying to understand the different, just as a summarization, we started off with understanding the different common methods of graduation, the wherein we talked about parametric formula, the standard table approach, and a graphical method of graduation. And any of these for all these three methods, we looked at what is the level of smoothness they are going to decide, what is the adherence to the data that is coming up from each one of them. Fitment for the fitment to the objective is something which we have looked at. The data, is it a large, are they applicable for large data sets or for small and scanty data sets? Are they more mechanized, or there is some level of flexibility or experts judgment that can go into these things? And we also looked at the validity of the method for each one of them. And how do I, once decided on the method, how do I typically use the chi-square test? What is the formula that I can go for testing out the goodness of it using the chi-square? And what is the way I would work out with the degrees of freedom for each of the approaches? And in case when I'm looking at the actual or graduated experience, what if my data set contains duplicate policies? How do I address the problem of duplicate policies? These are some of the things that we have taken up as a part of this session. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.